So yesterday we started on spectroscopy. The ultimate goal is laser diagnostics for combustion. I asked how many people had statistical mechanics. I think basically everyone thought they had, or maybe. How many of you have had a course in spectroscopy? Good. And how many of you are experimentalists using lasers in some kind of an experiment? Good. Okay, so you're motivated. Lasers were invented around 1960. They really started appearing in, say, fluid mechanics studies, maybe late 60s. So they've been around about 40, 45 years. And of course, what's happening is we get more and more wavelengths, more and more power, more and more capability. So we haven't really reached the top and going downhill yet. It's really getting better and better. Okay, so we talked about diatomic molecules because they're the simplest ones to deal with. We talked about how you start with classical mechanics, and then you just apply a couple of rules from quantum mechanics. You do not have to have a course in quantum mechanics to do spectroscopy. I emphasize that there are three parts of spectroscopy. There's line positions, line strengths, and line shapes. We spend a lot of time on line positions. In the end, you usually look this up or calculate it kind of easily. So this is more a question of understanding where those lines came from. So we spend a lot of time on line positions, but when you finally go to apply this stuff, you'll be spending more time on line strengths and line shapes. All right, so we're going to move from diatomics to polyatomics. Here's an example of a polyatomic. It's ammonia, kind of like three H's. It's really like a little tripod with the N at the middle here. It's a symmetric molecule. We'll always define an A, B, and C axis. The A axis is always the unique axis, the axis of symmetry. You can usually figure out what it has to be. It's the one that goes from up through the nitrogen, kind of perpendicular to the plane that contains the three H's. So you always find the A axis, find the center of mass, you can find the B and the C axis, and then you do your classical mechanics. But what's going to happen when we go to polyatomics? Well, first we have to do a little classification. We're going to start with rotations, and then we'll add the vibrations. Same pattern we did yesterday. Okay, so just in the way of a refresher, for diatomics, remember we write for the rotational energy, we use capital F. There's only one quantum number, it's J. It starts at 0. Now this would apply whether it's homonuclear or heteronuclear. The only difference being that one of those species is infrared active and one isn't. The rigid rotor term is right here, Bjj plus 1, where B is that h over 8 pi squared IC, inverse with the moment of inertia. This is the correction term. So when you're trying to learn something, pretend that's not there. Here's the rotational constant. It has units of wave numbers. Everything is in wave numbers when you're in low vibrational spectroscopy. Wave numbers is 1 over lambda. So if the wavelength were 1 centimeter, then the frequency would be 1 wave number. I noticed that Mike Pilling this morning calls them inverse centimeters. I call them wave numbers. There's the number of waves that fit into centimeter. We had selection rules that delta J is 1, where delta J is always defined as J upper minus J lower. And the line positions then have this very simple pattern, if you just look at this term, 2b J double prime plus 1. So in terms of the lower state quantum number. And therefore, you know right away that they have this regular spacing. This correction term D is small. It has some approximate value. For example, for NO, it's like 3 times 10 to the minus 4. And even when J is high, like 60, it's still only kind of a 1% contributor. So usually you can forget that term if you're just trying to understand things. Now what happens when we go to a polyatomic, which means 3 or more atoms? So we have to find the A axis, the B axis, the C axis. There's always in a classical mechanics problem 3 principal axes. The 3 principal axes are defined such that so-called products of inertia are 0. You can always find the principal axes. In the case of molecules, it's fairly simple to figure this out. And now we have to we'll classify these molecules in terms of the values of their, and relative values of their moments of inertia about these 3 axes. So A, B, and C are perpendicular. A is the unique axis, and they all pass through the center of mass. So now we're going to break them down into the linear, symmetric top, spherical top, and the asymmetric rotor. We won't talk about these very much. They're really tough. It gets really complicated. So linear, we're going to find out that the linear polyatomics are essentially no more difficult than the diatomics. Then we're going to go to symmetric tops, which is about, in which case the moment of inertia about B and C are equal and different than A. And we're going to find out that in some cases they're also pretty simple, but can be complicated. Then the spherical top turns out that the moment of inertia are equal, but we don't have to worry about the spectroscopy, as you'll see. Here's some examples. CO2, linear molecule. Acetylene. Carbon oxysulfide. Linear molecule, like a stick. It's like a stick that's just got mass at certain points. And we're going to find out that those molecules are pretty easy to deal with. We have to pay a lot more attention to the subtleties of these symmetric tops, which is like ammonia. Methyl fluoride, that's another one of these tripod things. Boron trichloride is like 3 in a plane. So you can put a plane through those 3 nuclei, and it'll still honor this relationship. So we look at the structure to decide which of these categories we're in, and that will dictate the equations we use for the energy levels. It will dictate our selection rules, and therefore will dictate the spectrum. So these are pretty simple. This has no dipole moment, so it's not microwave active. So we're in the rotational spectroscopy. That's the microwave region. They're not active. We don't have to worry about that. Now these are active and prominent. Water is common, but it's another big step up in complexity. So we won't deal with that. For the most part, when we deal with water, and we do a lot of work with water, been working on water for 20 years, you basically use tables of properties. They're already done. You just have to kind of understand them. You don't have to calculate them. So we can work with water, but we use a shortcut and use existing databases to get at the positions and the strengths. And then we do our own modeling of the shapes. So here we are, linear, carbon oxysulfide. So a structure like this. Here are some of the length between the nuclei. They tend to be a little bit more than 1 angstrom in length. Those are the masses. You can find the center of mass will be along this line. You can find it just about right here. And then you can evaluate the moment of inertia. Now, there's the moment of inertia about A, which is small. And because it's small, we actually neglect it, even though it is relevant in some cases. B is at any angle perpendicular to that A axis, and C is then orthogonal to B. Let's see. Now, B is always h over 8 pi squared I times the moment of inertia about that axis. Let's see what happens if I try to, let's see what happens if I advance this. No, it didn't work, okay. I think this will play as a movie. We'll see if it'll play that movie. I don't know if it will or not. No, too bad. It was going to be a nice little movie that shows how these things rotate about their axes. So, but it's obvious enough. The rotation about the B, all the rotation is perpendicular to B and just goes around and around. Ditto for C. And you can see that B and C are equal, which is part of the condition here. Now, the next level up is symmetric top. So now it's not linear anymore. But we have this condition that IB equals IC. So here's our example. 3 H's and an F. So it's like a tripod. So these 3 H's are in a plane, and F is perpendicular to that plane. So the one unique axis is through the F, through the C. I guess there's a C there. Must be methyl fluoride. So the axis is through F and through C for A, and then B and C are at any angle that you want. And you can convince yourself, if you spend a little time, that the moment of inertia about B and C are equal regardless of where you orient the angle around the A axis. Won't be able to play the movie again, which just shows it rotating around the A axis, rotating around the B axis, rotating around the C. So I would call this tripod-like. So whatever the axis is, we evaluate the rotational parameter. So whereas B, we've talked about, we do the same thing and we give a capital A with regard to the moment of inertia about the A axis, and C with regard to the moment of inertia about the C axis. So common definitions, just a question of the relative values of these moments of inertia. Now there are two types of symmetric tops. There's called prolate and oblate. And it has to do with whether or not A is less than B, which equals C, or whether A is greater. It's that simple. So there's one limit or the other. I sub A is either less than the others or greater than. So the prolate is when it's less than. And you can, this is an example. So you can see now the H's are light. So the rotation about the A axis is, moment of inertia is going to be smaller than when you look at the B axis and you see this heavy fluorine and carbon rotating around. So you can kind of see that this is an example of prolate. The oblate is the other extreme where IA is greater, and looks like I have that's the boron trichloride. So it's a planar molecule. Planar molecule. So now you can see that the rotation about the A axis is going to be the biggest one. So the equations are the same. It's just a question of deciding which of these two limits is in. Because what you're going to see is we're going to see an equation in which we see an A minus capital D. It's a question of what the sign of that's going to be, plus or minus. That's the only difference that it makes. Spherical top. Now, methane is a spherical top. So methane is a little hard to draw. The H's are at kind of diagonal corners of the cube. So it's got this high level of symmetry that leads to the fact that these moments of inertia are all equal. So it's a cube with the C at the center and the H's at the diagonal corners opposite from each other. And it takes a little more thinking to figure this out, but it has no dipole moment and therefore there's no rotational spectrum, so we don't have to worry about it anymore. It's out of the picture. Asymmetric rotor. So here's an example like water, H2O. So where would the A axis be? So the three atoms form a plane, and somewhere in that plane is going to be the A axis, and it's going to be the one that goes symmetrically through the two hydrogens and up through the oxygen. That would be the unique axis. Once I draw the A axis, you see that there is another element of symmetry here. If I rotate that thing 180 degrees, you can't tell the difference. So there's a symmetry factor, sigma of 2. The B axis then is just perpendicular to the A and ditto for the C. So that's an example of the asymmetric rotor. And again, for that molecule, it's so complicated that you go to some tables of the lines, and the notation for the quantum states is a little dense. But you can figure out from the table, it's important in the atmosphere. And so the atmospheric physicists have tabulated all of the line positions and strengths of these species that are active in the atmosphere. So you can look up right away and see if there's a line where you want it to be, or there's any competition with some other species. Okay, now we're going to talk about the spectra, starting again with the linear, and then we'll proceed on to the nonlinears. Here's 4 examples, ranging from acetylene here, CO2, HCN, that's the toxic one, that's hydrogen cyanide, carbon oxysulfide. Now, these two are symmetric. That is, there is an axis. If you pass the B axis here and you rotate it around, you can't tell which end it is. So they're symmetric. And why do we care about that? Well, if they're symmetric, then any motions along that axis will not produce a dipole moment, change in the dipole moment. Therefore, it's not going to be active. Well, we have to be careful now about perpendicular motion. So that's called a parallel motion. We'll define that a little bit later. So we care about the fact that it's linear. We also need to decide whether or not it's symmetric or not. It must be asymmetric to have an electric dipole moment. So again, you're watching this thing from a distance and you're seeing that little dipole magnifying up and down in some direction, which means it's a transmitter or a receiver. So it doesn't happen for the symmetric case. Now, in this case, what we're going to find is that there's still only one quantum number, J. There's still only one rotational constant, B, because we're not using A, and IC equals IB. And so we end up with an energy expression that looks exactly the same as before. So linear polyatomics are treated the same way as the diatomic. That's nice. So these nu, now strictly speaking, what should the units of nu be? The units of F and nu are wave numbers. Therefore, this should be nu bar. And again, we see that larger I larger moment of inertia means a smaller b, which means smaller spacings between the lines and smaller values for these frequencies. So big molecules with big moments of inertia are going to have more lines and they'll be closer together. And since they're closer together, that also means that at a given temperature, more states are going to be populated and you'll see more lines than if they were small molecules with large values of B. Okay, now, we always are interested in the structure of these molecules because the structure determines the moment of inertia. So how would we go about characterizing one of these molecules? Well, we have to, from the spectra that we're going to have access to. So the only thing you have to specify are the bond lengths. They're all along the line. You just have to decide what the lengths are. So if there's n atoms, there's n minus 1 bond lengths to be found. So if this was 3, then you'd have 2. So we have 2 lengths to decide. How can we do that? Well, from each spectrum, you're going to get one piece of information. So if you did the absorption emission spectrum, look at and to extract the value of B, you get the moment of inertia. Now, you need 2 lengths. So what do? You use an isotope. Remember, when the isotope doesn't change the charges, then it's the charges that set the lengths. So I can substitute in the mass, look at the spectrum, which will be shifted because the value of I has changed. So you use an isotope in order to get at the missing values of the moments of inertia and therefore the lengths. So that's how you go about it. If you have the spectrum, you can figure out the lengths. If you have the lengths, you can figure out the moments of inertia and the values of B. So here's an example of carbon oxysulfide. The final answer is 1.165 angstroms and 1.558. Center of mass is somewhere in here between the carbon and the sulfur. We would use 2 isotopes. We get 2 equations. So you'd use one isotope, and you'd get a value for B with that isotope and that moment of inertia. Then you'd use the second isotope, presumably, what did I say there? I used carbon, looks like I used oxygen 18. So you could use oxygen 16, then you use oxygen 18, and you get, they have the same lengths, but it has different moments of inertia, and therefore the lines appear at different places. I get 2 equations, 2 values for B, and I can solve for these 2 lengths, which are the same in both cases. Well, now we have to go to symmetric tops. It gets harder fast. Usually what happens when things get harder, you need more information to figure something out, and you'll come to a place where you've got to add another quantum number and another quantum number to help characterize things. So we almost always reserve J to be connected with the total angular momentum. But now we have to worry about the angular momentum about a specific axis. So here's my little cartoon of a spinning top. So the thing is spinning about its own axis while it precesses about another axis, probably the vertical. But that means it has 2 types of angular momentum. And the total is, so basically you've got this spinning, but it's precessing around, so that the J vector, if you had a vector, would be in this vertical direction. And so J is the total, and K is the angular momentum about the A axis, which can take on values, integral values, that range from plus J to minus J. So it can be equal to J if it's like aligned that way. Or it could be perpendicular. It can be arranged in different ways. So you have now 2 quantum numbers, and we're going to have to now be careful about what the selection rules are going to tell us. The selection rule was delta J of 1. Now we're going to have to worry about can K change or not. Now, what you do is you recognize that what's really quantized is the angular momentum. So you add up these angular momentum around the A, B, and C. That's the total, angular momentum total about the A, B, and C axis, and you call that J plus 1 H squared. So we're back where we were. No difference. But now we also have the fact that this one must be quantized also. So the angular momentum about the A axis is also quantized in units of K. And notice it's K squared. So again, K can be plus or minus, and it doesn't make any difference. Now, we go from the fact that the angular momentum is quantized to rewrite energy expressions and recognize that that therefore implies that the energies are quantized. So now the energy levels, which are now a function of J and K, you basically sum up the I omega squareds rather than the I squared omegas squared. And you can show with just a little algebra that the total rotational energy now is a function of both quantum numbers. And it's got the leading term that you're used to plus this additional term A minus B K squared. So now you see why we care about whether A is bigger than or smaller than B. In the limit that A is, in the limit that B is small, it'll be dominated by the moment of inertia about the A-axis. So anyway, you can examine this in its limits. So this is independent of the sign of K because everything goes like K squared. So some things are vector quantities, but then we use the magnitude of the quantity in the notation. So symmetric top, defined by this relationship. What are the rules? Well, delta J still turns out to be 1, and delta K will turn out to be 0. And the reason for that is that the rotation about the A-axis doesn't have any dipole moment. So there's not going to be any change in K when it absorbs or emits light. Nice, that's really nice. So what that means is that when you solve for the frequencies, and right now we're leaving out the distortion terms, we get the same answer we've always had. Independent of K. So as long as we're in this limit of a rigid rotor, we don't have any correction terms, and it's independent of K. So it's a very simple spectrum, same as a rigid diatomic. So where we get into trouble is when we allow it to be a little bit non-rigid. It gets more complicated fast. So when we do that, we're recognizing that it's non-rigid. Right now just because of rotation, but eventually because of vibration. That has the effect of changing the bond lengths, which therefore changes the moment of inertia. And that change then introduces these correction terms, and where now we have to get a little tricky, we have to pay attention to different notation. It'll be the correction term D, but now there's one for J, one for K, one for JK. So it's starting a little more complicated. So here we are, here's our energy expression F, with now the two main terms and these other correction terms. And when we look at the equation for the positions of the lines, we see the term that we're familiar with right here, plus some correction stuff. So you have to look to see where these corrections are going to show up. And let's see. Now, what do I want to say here? So, okay, each J has two J plus one complement. Now we're talking about the fact that K can range from plus or minus J through 0. So that's where the two J plus. So for each value of J, you can have two J plus 1 values of K. And therefore, that's why there's these subtle complications, even though there's only J plus 1 frequencies, because the term goes with J squared. So let's see. Looks like if J is 20, J squared is 400. I evaluated some of these numbers here, and I wanted to show you what the rotational spectrum would look like. So now that's, whenever you see wave numbers, that should be a nu. So nu in wave numbers, and these numbers are small because we're in the microwave region. So the transition, if we didn't have these correction terms, there would be a single line here corresponding to all the transitions from J of 1. All the transitions, meaning all the different values of K, which do not change in the transition. So, and the spacing would be 1.7, and that's because B is 0.85, so 2B is 1.7. Now what happens when we allow this, the fact that there's three values of K, 2, 1, and 0? Well, that means that this line right here actually has three contributions corresponding to the three candidate values of K. And so if you calculate their spacing, you would see that this bottom arrow here is 4 times 10 to the minus 4 wave numbers. So you have to recognize this spacing is 1.7. This maximum distortion is 10 to the minus 4. So unless you have very high resolution and you know exactly how to look for this, you won't even see it. So it's almost like they're degenerate, but they're not exactly degenerate. So that's what happens when we allow for non-rigid rotation of this symmetric top molecule. Now, this is a complicated looking plot, but I'll explain it to you. So remember, there's two cases. There's the case where IA is smaller than, or the case where IA is bigger than. And that just means A is bigger and A is smaller. So here's our expression for energy. It's just a question of the sign of this correction term right here. And so the easy way to plot all these different values is to imagine all the values of, for each k, imagine all the possible values of j. For k of 0, j can range from 0 up to any value. Once k is 1, j has to be at least 1, and so on. So once you get to k of 4, the minimum value of j is 4, because the maximum value of k is j. So, and the point being that for this is a k of 4, this is a j of 4. Here's the next j of 4. And the point is that the energy depends, energy of the state depends on both j and k. And the transitions that you're going to have will, remember, can only change j but not change k. So transition would be, say, between this line here, which is k of 4, j of 4, down to j of 4, k of, I did say that right. It has to go to, it has to maintain, I didn't say that right, excuse me. It has to stay within this manifold of k, so the spacing is between these two transitions of different j. But if you went for the same delta j for different k, you get a slightly different answer, and that's what we just showed you a minute ago. So it looks complicated. In most cases, these things overlap so much that you can almost neglect these correction terms. So what did we do? We looked at the linear case, which is simple. We looked at the symmetric top case. It's a little more complicated. We looked at the spherical top case, but we said that there's no dipole moment, so we're not going to worry about that right now. We looked at the asymmetric rotor, and we said, let's leave it alone. It's too complicated for us right now. Eventually, we always care about the partition functions, because it's the partition functions that are going to help us it's the energy and the partition function that are going to help us get the fractional populations. What do the partition functions look like when we go from the linear case to the symmetric top and so on? Remember, the rotational partition function is k over this quantity. And what's hc over k? 1.44. That's the conversion between wave numbers and degrees. So when I take this V and I multiply it by hc over k, I get a characteristic temperature. So, and that basically that ratio of T over theta R is essentially how many, you might think of it as kind of how many states are populated. And if that number is a big number, then life is a little simpler. And this is the symmetry factor. So now here's some examples for some molecules here. CO2, that's a symmetric linear, so sigma's 2. Here's ammonia, symmetric top. So if I have the A-axis, I can rotate that ammonia into 3 times and it looks the same. There's 3 positions that look the same. It takes a little more work, but you can show that sigma is 12 for the methane case. And now what is it for water? There's just 2 orientations about the A-axis that look the same for water. So we care about the partition functions, we care about the symmetry factors that go into those terms. Now, diatomic is proportional to T because you get a square root of T for each orientation, for each axis that it can rotate about. So now when you go to a symmetric top, it can rotate about 3 axes, A, B, and C. Now it goes like T to the 3 halves. So it stays at T to, so the linear is the only one that's the T. The rest are all T to the 3 halves. And whereas this is T over B, notice now we have a T over AB squared. So now A equals BC, so we can just do this in terms of a B. So basically the rotational constants appear in these denominators, but we now have a t to the 3 halves, and we have to represent all of the moments of all of the rotational constants. So that's the form of the rotational partition function for these types of molecules. So we're going to summarize. Linear diatomics and polyatomics and symmetric tops give to first order equal spacing at rigid rotor levels. So if you don't worry about this fine scale splitting, life is still pretty simple. Very high resolution is needed to monitor or measure these corrections. We use these spectra to determine the microscopic parameters of bond lengths and angles. And you can use isotopes in order to help understand these properties, because remember, the isotope changes the mass, but not the spacing, because that's determined by charges. Okay, that's rotations in 30 minutes. What about vibrations? Okay, we have to kind of do the same thing. We have to kind of introduce the number of modes and the types of modes and their strengths and so on. Here's an example. So HCN, that's a linear molecule. And what does it look like? This is some sort of, this is the absorbance spectrum, so this is 1 minus the transmission. What does it look like? I can't really read the notation, but it's probably wave numbers to the right. Remember, wave numbers are a measure of energy, so to the right means higher energies, and the R branch is always at the higher energy. So that's the R branch, this is the P branch. But there's something in here in the middle. Looks like it's probably a Q branch starting to make its appearance. So we'll have to figure that out. Okay. Some of this is kind of interestingly parallel to what Professor Pilling was talking about this morning. If you have n atoms in a molecule, then it takes 3n coordinates to specify the positions in space of all 3 atoms. So you have to have an x, y, z for each atom. So if you have n atoms, it takes 3n xyz coordinates to specify the instantaneous positions and hence orientation of the molecule. Total is 3n. And so we recognize that this molecule is moving through space, and we can represent the center of mass with 3 of those coordinates. And then if it's a linear molecule, we only have to worry about 2 angular coordinates. So it's 2 angular coordinates, but so it's a stick, and we only have to specify 2 angles to specify that. If it's nonlinear, we take 3 angular coordinates. The vibrations are what's left over. So if this is for vibration and it's a linear molecule, then I take 3n minus 3 minus 2 I have left over. There are 3n minus 5 vibrational coordinates that I have to, you can think of those as bond lengths if you like. 3n minus 5 vibrational coordinates or modes. If it's nonlinear, then it's 3n minus 6 because I have to subtract the next one. That's how many vibrational modes or frequencies I have to find. And it's usually pretty obvious. Now spectroscopy is a lot about notation and bookkeeping. And there's a system that's used to number these modes. And that's based upon symmetry and energy. So the notation nu1, and this is supposed to be nu, the notation nu1 is awarded to the highest frequency, that is highest energy, symmetric mode. So whatever the modes are, the motions, the one with the highest energy symmetry, highest energy in a symmetrical form, is called nu1. Now, nu2 is the second one, and so on. When I run out of symmetrics, I go into the asymmetrics. That's supposed to be, oh, that's the lowest frequency symmetric mode. Then I go into the asymmetrics. Now, this looks like a big list, but in fact, usually there's only a small number. So you do the symmetrics, then you do the asymmetrics. So frequently you'll find nu3 is the big asymmetric one. Those are the rules. And this says exception, but it's really just kind of an observation that these linear molecules, whether they're symmetric or not, the perpendicular motion, which I'll define in a minute, is always called nu2. All right, so now let's look at some examples. Oh, good, this one's working. It looks like it's almost too much for you, but okay. So we've talked about symmetric motions, how many modes there are, whether or not they're symmetric or asymmetric. Now we have one more classification, whether or not that motion constitutes a change in the dipole along the a-axis or perpendicular. So here's water, and it's a nonlinear molecule, so there are 3 vibrational modes. 2 of those are parallel, so this is a case where the H atoms are moving synchronously away from the O. This is a case where they're bending. That's called a bending motion. So this is a stretching motion. This is a bending motion. We use the word bending, but it's considered to be a vibration. And it has a smaller number of smaller frequencies, so it's called nu2 instead of nu1. And then one of these is they're out of phase. So remember, there's 3 of them. 1, 2, 3. I go through the symmetric ones, so this one's going to be called nu3. It's the highest energy asymmetric motion. It happens to have a higher number than either of these 2. But what's happening is, as this one is doing its thing, there's an oscillation in the electric dipole perpendicular to the a-axis. So that's a perpendicular mode. Why do we care? It's going to have different selection rules. Now here's a nice simpler one. Here's our linear molecule, symmetric motion of the 2 end atoms. Now this is symmetric bending. Those constants, so now it's bending like this. The CO2 is doing this, or like this. It's degenerate. That's another. Okay, that's another thing. For CO2, we have to find 4 modes, because there's both a B and a C axis here. It can bend around 2 different perpendicular directions, and we have to count those as separate. So that's called a symmetric bend degenerate. It has a low frequency. Here's the asymmetric stretch. So now, this is CO2, it's linear, so therefore when it's extending itself in a symmetric form, it's not IR active, whereas the asymmetric one is, and the symmetric bends are. So these are all infrared active, but of course at different frequencies. So here's a bit of a summary for some of these examples here. So let's see, I've got CO2, the vibrational modes of CO2. The highest symmetric one is called the symmetric stretch, nu1, 1388, not IR active. And this column says Raman active. So when a molecule is symmetric molecules, nature's been good. When a molecule is symmetric, it will either be IR active or Raman active. All modes have some kind of activity. Raman active means that it has some different selection rules. The process is a little different, but there is a spectrum. So now here's nu2, that's the symmetric bend. This is telling us how strong. So typically they'll tabulate these not active, strong, very strong. But here, when this is strong, this is not active. This is not active, then that should be active. So that's because it's a symmetric molecule. HCN, linear, but not symmetric. Therefore, when you look at the nu1, nu2, nu3, symmetric stretch, still active. Asymmetric stretch, weak actually. Now you can have activity in both columns. It can be both IR active, in fact it is, both IR active and Raman active. But usually weak is accommodated by strong and so on. So there's a lot of stuff there, but I think it's understandable if you have time to kind of think through it. More notation. So when we have vibrational motion and the primary quantum number, or the primary selection rule is delta V is 1. When it changes by 1, that's called the fundamental. When the quantum number changes by 2, it's called the first overtone, and when it changes by 2, it's called the second overtone. In the simplest case of a harmonic oscillator, these would not occur. But because the molecules are not exactly harmonic oscillators, they do occur. They tend to be weak. So they do exist, they're just weak. So that's when one quantum number changes. So the notation is, that's called the nu I mode. This is called the 2 nu I mode, meaning that the quantum number for mode I changes by 2. Quantum number for mode I changes by 3. And when it's changing, the quantum numbers for the other modes don't change. That's the simple rule. Combination bands. Now it's a little more complicated. We're going to allow that it is possible for two quantum numbers to change. And if we call this the nu 1 plus nu 2, they both change by 1. They both go up or they both go down. 2 nu 1 plus nu 2 would mean that this one changes by 2 and this one changes by 1. Difference bands mean that one goes up and one goes down. So that's a lot of notation. The fundamental bands, the combination bands, the difference bands, but it's all notation. As soon as somebody says, I'm going to watch the nu 1 minus nu 2 band, well, I know the frequencies because I know nu 1 and I know nu 2 and I know what can happen. And then if you look at the molecule and the type of molecule and its character, you can figure out what the selection rules are and what the spectrum is going to look like. Okay. Now, partition functions. In the limit that we separate the forms of energy, rotation, and vibration, each one has its own partition function. So the rotational partition function is separate from the vibrational partition function to first order. The harmonic oscillator expression for a partition function is 1 minus e to the minus this number right here. Now when you have multiple modes, all you have to do is take the product. So if, for example, ammonia, which has 6 vibrational modes, the overall vibrational partition function is simply the product of the individual partition functions, except 2 of them are squared. Why are they squared? Because they're degenerate motions. You have to count them twice, these 2. So you see the value of thinking about the energies separately. The rotational energy is separate from the vibrational energy. The activity in the vibrational mode is independent of the other one. That allows you to separate the energies, which means separating the partition functions. Keeps everything a lot simpler. Relative strength. In general, the fundamental bands are much stronger than the combination bands. If you have a relatively harmonic molecule like CO, then the overtones are going to be quite a bit weaker. They go down by about 100 every time you change from the fundamental of the first to the second. So the closer you are to an SHO, the more close you are to being actually forbidding the overtone bands. And harmonic molecules, on the other hand, like ammonia, may have only a factor of 10 difference between the fundamentals and the overtones. Less forbidden. Okay, there's one special case. It's called Fermi resonance. Accidental degeneracies. Molecules like resonance. If 2 molecules come together and they have equal vibrational spacings, it's very easy to transfer quanta. Similarly, within a molecule, like CO2, turns out that 2 times the value of nu 2, that energy, is very close to resonant with the nu 1 mode. So that just means they talk to each other a lot. And as a result, you can get a two quantum first overtone transition in CO2 much more easily than usual. That's called resonance, Fermi resonance. Okay, we're going to look at the rho vibrational spectra now. So now we're going to put these 2 things together. We're going to look first at the linear polyatomics. Here's our expression for T. It's the sum of G. Okay, that should be G of V. Every time there's a vibrational quantum number, it's V, not nu. So there's the quantum number V, quantum number J, F for rotation, G for vibration, T for the total. Remember, we have 2 kinds of bands now. We've got to be a little careful. We have 2 kinds of bands, symmetric and asymmetric. Symmetric, we're not going to have any activity. Therefore, this diagram is only for the asymmetric stretch. So here from V double prime of 0, remember V prime for upper, V double prime for lower. Here's our initial quantum state. The selection rule is delta V, that should be delta V of 1. Delta J can be plus or minus 1, meaning that you can only have P and R branches. And this says that the other modes don't change. So in other words, if this nu sub I changes by 1, nu sub J does not change. They don't talk to each other. So this is the spectrum you would see for one of these modes. There'd be a null gap right there. R branch, longer frequencies, P branch to the left, and in the limit where it's basically a rigid rotor, these lines are equally spaced at 2B. Now okay. So there's no parallel band for CO2 because of its symmetry. Now I'm just trying to show you some actual stuff. This is a parallel band of the linear molecule CO2. So is that the symmetric stretch or the asymmetric stretch? It's got to be the, you can't have, it's not there for the symmetric stretch. So this is representative of what happens in the laboratory. CO2 is kind of a big molecule. That means the moment of inertia is big, values of B are small. So the lines get close together, and then unless you have good equipment, all these lines look like they just kind of fall on top of each other. Especially this branch here, which would be the R branch. Sometimes frequency goes to the left, which means wavelength goes to the right. Yes, question?
Is that the Q branch you were talking about in the middle? Or
No,
is it...
no. Remember, this is transmission. So you have to kind of be careful. Transmission. So the absorption is going down this way.
Oh, okay.
So if there were absorption, I would have seen another
Yeah.
right there.
Okay.
So you have to be careful whether you're applying transmission or absorption or absorbance. So, you can understand this stuff. Now, the fact that you can't observe all of these lines doesn't mean they're not there. It just means the equipment that you're using doesn't allow you to see it. Okay, now let's see. Case 2, perpendicular bands. Delta V is still 1. Delta V sub I is still 1. Delta J is plus or minus 1 and 0. Now we get a Q branch. And so now you're down here in, say, J. Now you can also have a Q branch transition. So you can have the R, you have the Q, you can have the P. In the limit that B prime equals B double prime, all of the Q branch transitions are at the same place. They're not distinguishable. Only when they differ. So Q is given by a constant plus this delta B JJ plus 1. So only when these two differ. And why do they differ? Because remember, we have the expression B sub V is BE minus alpha V plus a half. So it depends on the value of alpha. Usually that's so small you can hardly see it. But they are, if you look closely, the Q branch is the branch that's distributed. Here's the case then. So this now is, okay, so this one is a real Q branch. Now this is absorbance going vertical upward. Now, why do we have a Q branch? Because it's a bending mode. It's perpendicular. It's a perpendicular band. So the HCN is linear, but it's bending. And that results in a perpendicular contribution, which has these selection rules. Okay. Symmetric top.
Professor?
Yes.
Question?
Yeah.
Previous slide, there's a notation of impurity.
Okay, so this is a laboratory spectrum. All of a sudden, remember now, absorbance is going up. So all of a sudden, there's some interference there, which this person has attributed. Okay, the question is, what's this perturbation here? Why is it labeled impurity? Because this is a plot of absorbance measured in a static cell, and there's probably some impurity. Now, yesterday I showed you some examples where there was an isotope. So this is written impurity, and it probably is because it's pretty strong, but you also get something similar when you have isotopes. You get an interference. So there's a difference between the spectrum of pure HCN and impure. So let's see, symmetric top. So we're going to symmetric top now. Remember, that's the complication there is now we have a new quantum number that we have to add in. And remember, we always categorize by parallel and perpendicular. Let's start with parallel. It's easier. Selection rules for the parallel are delta V sub I of 1, good. Delta J plus or minus 1 or 0, good. That just means it's the same as the bending modes of a linear. Delta K of 0, So when it's a parallel mode, that just means that there's no change in K, and it's like it's not there. So life is the same as it was for the bending mode of the linear for the parallel band of this symmetric top. So it's easy to kind of, this is what it looks like. This is an absorption spectrum. And these are the components. So these are the components for different values of K. It's kind of easier to think about. Imagine K is 0. What's the value of J when, what's the value of J? What's the minimum value of J when K is 0? 0. So when you go up in K, you change the minimum value of J, and that's why you begin to see some holes in the spectrum here, around here. So you can now imagine that they all add up, and you see something that looks like this, except that the spacing may be, the splitting of these lines may be so small you can't see it, but they're all there. You can calculate it. You may not be able to see it, but you can calculate it. So here's the parallel band, and here we are now. Let's see, this is transmission, so it goes 100%. There's the absorption right here. It peaks at some value of J, peaks at some value of J. The R branch is always a little stronger absorber. but it peaks at the J, which has the greatest population, and there's the Q branch, unresolved. So it looks like it should. Here's a second example. This is this methyl iodide. Tripod-like molecule, 4 atoms, 5 atoms, understandable. So notice that this is frequency. So to the right, that's the R branch. To the left is the P branch. You can begin to see the structure in the P branch. So apparently, those lines are spacing out a little bit, whereas these are kind of congested. You can't. It's the limited resolution of the equipment that's causing this problem. Now, what about the hardest one? Symmetric top, perpendicular. Now we got the selection rules of delta V sub I of 1, but now and plus or minus 0, but now K can change by 1. So all of a sudden it just gets a lot harder. R branch is still delta J of plus 1, P branch is still delta J of minus 1, Q branch, etc. But now for each case, delta K could be plus or minus 1, and you end up with more complicated expressions. So you end up with lots of candidate lines. In the end, you would see this is the energy level structure. Whereas before, we stayed within the K manifold for delta J. Now you can cross over. So it's lots more combinations. And so you have to calculate them individually, and they look like this, and you add them all up. This is a blow-up. Okay, now if we just look at one of these Q branches here, this was a high-resolution experiment, it looks like, where they were able to separate those lines. So that's just part of the Q branch structure of a perpendicular band. So I think we're about almost on time. So let's say you have typically I do this. I give the students a spectrum, and then I'll say, identify the molecule. What can you do? One of the things you'd look at, you'd say is there a Q branch? No Q branch. Oh, that's nice. Is there a Raman activity as well as infrared activity? So all of a sudden, you do your detective work, and you can kind of figure out something. Is it a linear molecule? Is it a symmetric top? Is it a bending motion? You can figure out by knowing the Raman. So for example, if the Raman and the IR are exclusive, it's a symmetric molecule. If there's a Q branch, there's only certain categories that can have a Q branch. It's got to be the bending motion of the linear molecule or the characteristic of the symmetric top. So that's kind of, you can figure it out. So I think I'm going to stop there. So we've talked about, in one quick 50 minutes, we talked about polyatomics. We've only talked about rho vibrational. Haven't talked about electronic transitions. As soon as you step into electronic transitions, everything gets a lot harder. So it gets harder when the molecules get bigger, and it gets harder when you go from rho vibrational to electronic. So we'll have to spend a lot of time. But remember, we're talking about line positions, line strengths, line shapes. Next hour, I'm going to try to introduce line strengths, and we'll only spend a little time on this. Where do the line strengths come from? You need to know them. That's a measure of the strength of the transition. And then you have to know the shapes. We'll do that in 1 hour also. So by the end of today, we'll have kind of dealt with how do you get quantitative about spectra. There's the positions now, and you'll know something about where the strengths come from and how we characterize the shapes. Any questions? Going too fast? Too slow? Here, Professor Poinsot asked, am I going too slow? And somebody raised their hand. Going too slow, I guess he said. One person raised his hand. Am I going too slow? Okay. It's just trouble is it's just accounting. It's just lots and lots of notation. And why do they do this? Because this compact notation tells the spectroscopist almost everything he or she needs to know. This little compact notation tells you what kind of a molecule it is and what its rules are going to be, what state you're in, what's allowed. Tells you everything, but it's very compact and dense. It's a little bit like reading Professor Foreman Williams' book or Professor Law's book with all the notation. Or if you've ever had a course in radiative heat transfer, notation just kind of blows you away. That's what spectroscopy is like. But to actually use it, you don't actually have to know that much. If you just kind of are smart enough to avoid certain problems, a lot of stuff's tabulated. You just take advantage of what's been done before you. Okay, so I guess we will resume at about, I don't know, maybe 10 after. Okay.